Okay, so we're going to start our next unit on exponents. So it's a nice extension off of the work that we did last year on exponent laws. So today what we'd like to do is actually just to go through and review everything that we know thus far about exponents. So we're on page 61 in your workbook. Previously, a lot of our work had actually been working with numerical bases, and so we'll extend it a little bit using variables as bases, but essentially it works exactly the same thing. We also previously had exponents that were natural numbers or whole numbers. Now we're going to extend that as well into integers, so negatives as well as positives, and also rational exponents as well, so perhaps decimals or fractions. So let's take a look then. So exponents, previously we've always talked about exponents as being a way, kind of a short form to show repeated multiplication. So specifically, we're looking at multiplying the same number by itself over and over again. So for example, we might have 2 times 2 times 2, which is also known as 2 cubed, and that is exponential form, so repeated multiplication, or we might also say the expanded form as well. That repeated multiplication is 2 cubed. And we can also do the same thing with variables. So if we have a cube that has a side length that is a, we could say that it is a times a times a, or a cubed. And so what we know is just some review of terminology. A power, a lot of times people talk about a power as being the exponent, but technically speaking, the power refers to the whole thing, meaning the base and the exponent is the power. The base is the number that you are multiplying by itself. An exponent tells you the number of times you're multiplying the base by itself. So let's just write this out. These are a couple of points that we've always talked about. So the fact that the exponent tells us the number of times the base is multiplied by itself. And so with that, then, if we looked at class example number 1, the base being 4, the exponent being 5, so then what we know in expanded notation, so it doesn't actually ask us to write the expanded notation, the repeated multiplication, but that kind of shows us that we know what the base and the exponent each are. So the base being 4, and the exponent says repeat that 5 times, so 4 times 4 times 4 times 4 times 4. So the one other piece that's important to note before we go on to that second example, B, is the base is directly below the exponent, or it is the base is also, or it could be, everything in brackets if the exponent is outside. And that's a really critical one, especially if we're talking about negative. So the difference then in example B is that exponent 6 is outside the bracket. Everything inside brackets, the negative and the 3, are inside, which means that the base negative 3 is multiplied by itself 6 times. So negative 3 times negative 3 times negative 3 and 6 times. And so you notice with multiplication, again, I can use the little times symbol that looks like an X, or I can use brackets, parentheses as well. It's saying exactly the same thing. So versus the difference, if I had minus 3, to the 6 and no brackets, then the base in this particular case is only the 3, not the negative. So if I was expanding this, it would look like, it's almost like negative 1 times 3 times 3 times 3 times 3 times 3, and missing one more 3. So we've got 6 threes being multiplied by itself, but the negative is not included as the base. Okay. For example, number 1, C, for x to the y, of course y is our exponent and x is the base, but because I don't know the actual value of y, I would not be able to put that into an expanded form. Okay. So let's take a look in this case. It talks about the term coefficient, which you guys should be very familiar with. We talk about the expression 7p cubed, the coefficient being 7. And this is also a nice example for us to talk about the base here, the base directly below the 3, meaning it is just the p, which is the base. At the same time, we could also say if I've got, or if you use that same example I had previously, minus 3 to the 6. So there's no variables in this particular case, but somebody could also say that negative 1 is the coefficient in this particular case being multiplied by, it's the value that's being multiplied by the power. Okay, so for class example number 2, state the coefficient for each of the following. So that is the value that's being multiplied by the power. So for A, of course, we're looking at 8. And if you even want to hit pause and go through B and C on your own and then come back, that would be great. Okay, so B being multiplied by the power, our coefficient is negative 3. And for C, this one's kind of a tricky one because we want to recognize that it's the same as 1/7 times A to the 8th. So my coefficient is actually the 1/7. Okay, and repeated multiplication, 7p cubed, again we mentioned directly below the exponent is the base, which is the p, and that is why the p is the one that's being repeated, whereas the base being everything inside brackets here, 7p all cubed, meaning the 7p is being multiplied by itself, so 7p times 7p times 7p, or they've actually just written it out all separately, 7 times p times 7 times p times 7 times p, or rearranging it further using the commutative property, which essentially says that the order doesn't matter when you multiply or add. Of course, we're only talking about multiplication in this particular case. And so it's pretty typical that we're actually going to evaluate any numerical portion. So that coefficient portion, 7 cubed, is 343p cubed then. Okay. So in this case it says write each of the following as repeated multiplication. So let's go through that first one together and then you can hit pause and come back and check your work. So for A, we're looking at, of course, we're looking at equals 3 times, so you can use the times symbol, or I can use a dot, or I can use brackets. It's just all meaning the same thing. So the base for the exponent 4 is the A, so we've got 3 times A times A times A times A, 4 A's there, and then times B. Excellent. And so again, as repeated multiplication for, I'm just going to hop over to C here, moving to the right. So the base for this exponent outside of the brackets, inside the brackets is the AB. So in this case, we've got 3 times A times B times A, whoops, those didn't turn out, times A times B and times A times B, and again times A times B. And so those A's and B's can be rearranged as well, so that all the A's are together, all the B's are together, or I'm totally fine you leaving it like that as well. So just hit pause right now and then finish with examples B and D. Okay, so if we take a look at B, the base for that exponent 4 is just the B because there's no brackets. So we've got 3 times A and then 4 B's being multiplied together. In letter D, example D, all of 3A and B, that whole product is part of our base because the exponent 4 is outside, so 3AB times 3AB times 3AB times 3AB, or you can insert the times between all of those as well. Okay, evaluating the powers just means that we're working with our bases that are numerical, that are integers or rational numbers, and so it might mean that you are expanding it out into repeated multiplication. In some cases, you might already know what the answers are. So 10 cubed being 10 times 10 times 10, so that is, of course, 1,000. And if you're not sure, then just working left to right. 10 times 10, 100 times 10 is then 1,000. 3 to the 4th, again, 3 times 3 times 3 times 3. We can work left to right. Another way that works nicely as well that I often suggest is pairing off those 3's, because if we were to go left to right, we've got 3 times 3 is 9 times 3 is 27, and a lot of people get stuck on that 27 times 3. But if I was to pair them off, we've just simply got 9 times 9, and most people are pretty quick to see that 9 times 9 is 81. So here again is that scenario of what is my base. So -6 all in brackets squared means that the base -6 is being multiplied by itself. -6 times -6 is positive 36. In the case where I don't have brackets, the base is only the 6, so we've got like a -1 being multiplied by 6 times 6, so the answer, the product, is actually -36. So that makes a huge difference in recognizing what is the base and whether or not that exponent applies to the negative or not. Okay, the zero exponent. So going back to the first of our exponent laws, so if we complete the pattern below, so 10 to the 4th is 10,000. The quick way to do that, of course, many of you guys recognize, was anytime we had a base 10, the exponent should tell you the number of zeros we have. So 10 cubed is 1,000, 10 squared is 10 times 10, or 100, 10 to the 1 is 10, 10 to the 0, then, and this is this is a little bit trickier, but again, from a pattern perspective, perhaps you recall, hey, I'm dividing by 10, I'm dividing by 10, there's 1 less 10, factor of 10, so again, dividing by 10, and 10 to the 0 is 1. So similarly, 3 to the 4th we had just done above, which is 81, 3 cubed is 27, and that's 1 less 3 being multiplied, so we can say that we're dividing by 3 each time, and so following that pattern, 3 to the 0 then is also 1. So at the end of the day, that general rule is anytime we have a base to the exponent 0, a to the 0, for example, is equal to 1. And the one thing that they're missing here, though, is that condition. So turn that period into a comma. A to the 0 is 1, provided that a does not equal 0. So 0 to the 0 is undefined. And the reason for that is developing that exponent 0 has to come from this division piece. So there's no way to actually expand and show an exponent 0 as repeated multiplication. The only way to get there is through a pattern, and every pattern involves some kind of division, and the one thing we cannot divide by is 0. So 0 to the 0 is undefined. Okay, so evaluate the following. So 6 to the 0, 1. Negative 9 to the 0, that's the whole base to the 0, is also equal to 1. Minus 9 to the 0, tricky, because that's like negative 1 times 9 to the 0. So negative 1 times 1 is, of course, negative 1. So paying attention to what is our base. In this particular case, 2 times, and 6 squared, we don't actually need to know that that's 36. Obviously, I know that you guys all do, because the exponent 0 is on the outside, the base is not 0, so I know that this whole piece right here is just simply 1, so then 2 times 1 is simply 2. Okay, let's go back to our exponent laws then. And so we have a number of exponent laws that we had gone through last year. So there were 5 of them in addition to that 0 exponent law. So they show it here with numerical bases, which is mostly what we worked with last year, though we did touch on variable bases as well as our exponent law itself. So the thing that I want to remind you guys that we talked about constantly last year is, if in doubt, expand it out. So I know that lots of people have the exponent laws memorized. I know as well that lots of people tried to memorize the exponent laws and unfortunately ended up getting mixed up. But if you are ever in doubt, unsure, trying to decide, should I guess, should I not guess, it takes you literally seconds to expand it out, simplify that example, and you will quickly see what the pattern is and confirm whether or not your guess was correct or not. So for example, if I've got then that first one, 8 cubed times 8 squared, so expanding it out, 8 cubed is 8 times 8 times 8, and times 8 squared, 8 times 8. So we can see we've got 5 8s being multiplied together, so 8 to the 5th. So what are we actually doing then is we are adding those exponents together. So similarly, if it works with numbers, it's going to work with variables. So again, if you're stuck with variables, go back to numbers. And so that's going to help confirm things for you. So they're leaving a few things fill in the blank for us. So we're talking about a to the 5th or a to the 3 plus 2. So if I've got a to the m times a to the n, then we've got a to the m plus n. And of course, in words, if you felt like it would help to write it out in words, when we're multiplying powers that have the same base, keep the base and add the exponents. So again, if you're not sure, and expand that out. And so even if we were coming to the side here, if I've got 3 squared times 2, let's go with 2 to the 4th. Can we combine those? Well, if we look at what it looks like expanded, these are not the same bases. So I can't clean that up. I can't say it's 6 to the exponent of something because we could pair these up and have 2 6s, but then we've got the other 2 2s. I can't say it's 6 to the 6th. I can't say it's 3 to the 6th or 2 to the 6th. That is simply as much as we can do in terms of evaluating our exponents or trying to clean that up as a single base. So 3 squared times 2 to the 4th does not apply. So that product law is only when the bases are the same. Okay, 8 cubed divided by 8 squared is easier to see if we rewrite it in kind of fraction form. So our dividend 8 cubed expands to 8 times 8 times 8 divided by 8 squared, or 8 times 8. And so remembering that we could kind of split these up and say, well, 8 over 8 is really just 1 over 1. 8 over 8 is really just 1 over 1. So I'm just left with that single 8 over 1, or 8 to the 1. So what are we actually doing is we're taking the exponent of our dividend and subtracting the exponent of the divisor. So again, 8 cubed divided by a squared. A over a is just 1, provided that a is not equal to 0, and same thing here, so we're left with just a to the 1, or a cubed minus a squared, and this is the answer. And we're just going to write in as well, a is not equal to 0. So in variables, then a to the m divided by a to the n, and that can be written left to right or as a fraction. And so we're looking at a to the m minus n, and you can see that condition right there, that the base cannot equal 0 for a quotient law. Okay, if we've got a power of a product, so you can see our product is our base right there, and that exponent cubed, so 8 times 7 times 8 times 7 times 8 times 7. If we rearrange using the commutative property and change that around, then we've got 8 times 8 times 8 times 7 times 7 times 7, and that's also known as 8 cubed times 7 cubed. So similarly with a and b, if we replace that 8 and 7, so we've got a times b times a times b times a times b. That of course could also be written as ab cubed, and a times a times a times b times b times b, and so that's a cubed times b cubed. So ab to the m is the same as a to the m times b to the m. So a lot of people think of it almost as if you're distributing that exponent to each of the factors of your product. And it's important to note that this works for a product, and what we'll quickly see is it works for a quotient. It does not work for addition or subtraction. So taking a look at power of a quotient law, then 8 sevenths all cubed, so that whole quotient 8 sevenths is our base, so 8 sevenths times 8 sevenths times 8 sevenths, also known as 8 cubed divided by 7 cubed. Similarly, a over b all cubed is a over b times a over b times a over b, or a cubed over b cubed. So again, it's almost like distributing that exponent, so a to the n divided by b to the n, and in this case our divisor b cannot equal 0. Okay, the last one of course is power of a power law. So we've got the power 2 on top of the other power 8 cubed, and so the base for the exponent 2 is 8 cubed, so we're looking at 8 cubed times 8 cubed, because the exponent 2 tells us to multiply the base 8 cubed by itself. If we expand it further, we're looking at 8 times 8 times 8 times 8 times 8 times 8, or 8 to the 6, or 8 to the 3 times 2. So we realize in this case we're multiplying those exponents together. So a cubed all squared is a cubed times a cubed, or a times a times a. Whoops. And then times a times a times a, so we're talking about a to the 6 or a to the 3 times 2. So a to the m to all to the n is the same as a to the m times n. Okay, great. So let's take a look then. 3 to the 4th times 3 squared, so that is our product of powers rule, and so we're looking at 3 to the 4 plus 2, or 3 to the 6. If in doubt, expand it out. 3 times 3 times 3 times 3 times 3 times 3, and you can see that that is 3 to the 6. So there's our 3 to the 4th times 3 squared. Similarly, in this particular case, negative 2 is the base, and that's consistent for both of them. And so In this case, we're looking at negative 2 still stays the base, and 5 minus 3 is 2. If we wanted to expand it just to be sure, we're looking at negative 2 times negative 2 times negative 2, and 5 negative 2's on top, 3 negative 2's on the bottom, and negative 2 over negative 2 is 1. There's another 1, there's another 1, leaving me with just negative 2 times negative 2. And then 5 squared all cubed is the same as 5 squared times 5 squared times 5 squared, because that cubed, the exponent 3 is our exponent, and of course it is, and the base being 5 squared, so that's what's being repeated. So then if we expand it further, just to be sure, then we've got 5 times 5 times 5 times 5 times 5 times 5, or 5 to the 6. Okay, the evaluate piece, certainly I wouldn't expect you to know 3 to the 6 offhand. Some of you might happen to know what that is, or you can use your calculator for that one, 729. The next one I would certainly expect you to know without your calculator, so this is our evaluate portion. So negative 2 squared, negative 2 times negative 2 is positive 4, and 5 to the 6, that's probably going to be a calculator one, and that is 15,625. Okay, so same things are going to happen when it comes back to having a variable base. If in doubt, expand it out. Things to note as I take a quick look at these examples: anything that has a numerical portion to it, so part of your coefficient. So remember here our coefficient is actually 1/4, our coefficient of 2. Those portions should be evaluated. Okay, so take a moment, just hit pause and work through all of those examples, A through L, and then we'll compare notes in a moment. Okay, let's take a look at A. So here I'm multiplying powers that have the same base, so A times A times A times A times A times A times A. So altogether we're looking at A to the 7th. X to the 6 times X. Remember that's the same as X to the 1. And so in that case we've got X to the 7 for the same reason when we expand that out. Again, expanding this piece, knowing that B to the 0 is just going to be equal to 1. So with that, I'm going to need a caveat that B cannot equal 0. Otherwise, this whole thing would end up being undefined. For D, x to the 8th divided by x to the 4th is x to the 4th. So if we were to expand it, we'd have 8 x's being multiplied in the numerator, 4 multiplied in the denominator, and we could simplify and make a bunch of 1's with those. For E, same thing would happen. We've got 10 y's being multiplied in the numerator, 2 being multiplied in the denominator, and again making 2 1's, leaving us with y to the 8th. For F, A to the 12th, G, y to the 25th, H, x to the 9th over y to the 9th, I, and we're talking about c squared over 4 squared, which is also known as c squared over 16, and s times t, all to the 6, so the whole base is st, and that's being multiplied by itself 6 times, so we'll end up with 6 s's, so s to the 6th, and t to the 6th. In this case for k, we're talking about 2 to the 5th times a to the 5th, and we want to always evaluate the coefficient portion, so we're looking at 32 a to the 5th, and for L, we're looking at -3 all to the 4th times p to the 4th times q to the 4th. Again, evaluating that -3 all to the 4th, and that's positive 81 because we would have 4 -3's being multiplied by each other. Okay, please let me know if you have questions along the way, and we'll continue with the next lesson then.